What we are working on for today is our arithmetic sequences. So last class we talked about basic sequences, talked about the recursive definition, which is the one that connects it to the term before it. So now there are two specific kinds of sequences we're going to be dealing with, and our first one is your arithmetic sequence. Arithmetic sequences mimic a linear function. So you can tell you have an arithmetic sequence because to get from one term to the next, you are going to be constantly adding the same number. Just like with your linear functions, you're always adding the same number to get you to your next y value. So like for example, 4, 6, 8, 10, 12, 14, so on and so forth. That's an example of an arithmetic sequence because all I'm doing is I'm adding 2 to get me to my next term of that sequence. So that's how we know it's arithmetic. So let's take a look at our example here. This is kind of a word problem that demonstrates our arithmetic sequence. We got Evan is saving money to buy a new toy, and she already has $12 in her account, and she gets an allowance of $4 per week and plans to save $3 of that in her account. Fill out the table for the amount of money Evan has after n weeks of saving. So after she has saved for 1 week, how much money does she have in her account? $15. That $12 she started with, that would be at 0. That's like at the beginning of time for this situation here. That's when she had $12. So after the first week, she put $3 more in there. So that's why after the first week, she has 15. How much would she have after week 2? And then 3, 4, 5, 6, and 7. 33. So there's our table for this. Each week she just keeps adding $3 more. Kind of hope that toy's not very expensive, otherwise it's going to take her a while to save up for it. So part B, they want us to write a recursive definition for this sequence. So again, a recursive definition needs to have 2 parts. You have to state what your first term is, and then you state what you're doing to the previous term to get you to the next term. So what is our first term here? 15. If you look at the 1 in your table, your first term there is a 15. If they said a of 0, that's when we would use 12. But for 1, it's a 15. So then our recursive definition, the other part of it, we take our previous term, so our previous week's amount, and what do we add to it? 3, so plus 3. And again, remember this right here, that stands for the previous amount. So you're always taking the amount before it, you're adding 3, and then you're adding 3, and you're adding 3. So Evan proposes the following explicit formula for the amount of savings, A, as a function of the number of weeks saved, which is n. Is this formula correct? A little note there is we should test it. So first thing, we got a new word here, explicit. What an explicit formula means is it looks a lot like your function rules. That's your explicit formula. So for our arithmetic sequence, since it mimics a linear function, your explicit rule is going to look like it's an mx plus b form. So that's why if we look at the rule down here that she came up with, this looks like your mx plus b form. That's our explicit rule there. So your explicit rules always look like your function rules. So they want us to test this. So in order to test it, I'll start with week 1. And I'll plug a 1 in for all of my n's. So what do we get here? 3 times 1 plus 15. Is that the same thing we had up above? No. So is this the correct formula? No. That is not the correct formula. So the way we would come up with this rule is actually a formula you will be given on your Regents exam. If you flip back to the inside cover of your packet, you've got this little list here. These two formulas that I have here in boxes, you are given on your Regents exam reference sheet. So you don't have to memorize them, but you do have to be able to use them. So we use these rules to write our explicit formulas for both our arithmetic sequence, which is the first one, and then your geometric, which we're actually going to be talking about on Friday. So, a couple little definition things here. A of 1, which is right there in our formula. We learned that last time. When it's got that 1 there, that means it's talking about its first term. So you use your first term to help you figure out your formula there. N represents the number of terms, and that's right there in that part of the formula. Your D, this is new, that is your common difference. That's whatever you're adding or subtracting to get you to your next term. That's what we refer to as our common difference. It's common because you're always adding or subtracting the same number, and then it's the difference because it's how far apart the two numbers are. So our common difference there. And then my other one, A of n, that just refers to the last term, which it's whichever term you're looking for. So if you're looking for your 4th term, you would have A of 4. If you're looking for your 7th term, you'd have A of 7. So that's our formula. We're going to be using that a little bit in class today. So let's go back to our note page. Let's come up with the actual correct explicit formula for Evan's problem here. So we'll use function notation instead of the subscript that we had on the back of that sheet. So all you have to do is change it, as I said, to A of n instead of A sub n. That's the only difference there. So let's come up with our rule. What was our first term again? 15. In those parentheses there, the n minus 1, n is going to stay as n because I'm not looking for a specific term. I'm just trying to write a general rule for this. So we don't know what n is. We want to leave that as n for right now. But we do know our common difference. What did we add each time to get us from one term to the next? Plus 3. So my d is a 3. And you always want to make sure you put parentheses around it because let's say, for example, you had a negative d value and you're writing it in your formula and you don't put parentheses and just put minus 3, then a lot of people, instead of doing what you're supposed to be doing, which is multiplying, they end up subtracting 3 at the end. So you always want to put it in parentheses because now you would be multiplying it. So that's a very important thing. So we'll distribute our 3 here. I know it's in the back, and you're not used to seeing it back there, but it's the same rules as if it were in front of the parentheses. You're still going to distribute that. So I get 3n minus 3 when I distribute, and still our 15 in the beginning. So adding our like terms, we would get 3n plus 12. That's the rule she should have come up with. That's her explicit formula for her situation. So arithmetic sequences are ones where the terms in the list increase or decrease by the same amount given. So that's just a little refresher of basically what we were just talking about before. It's always going up or down by the same number. So example 2, an arithmetic sequence is given using the recursive definition. B sub 1 is negative 3, so that means our first term is a negative 3. And then down over here is the other part of our recursive. To get your next term, you take the previous term and you add 6 to it. So which of the following is the value of B sub 4? Which means we're trying to find our 4th term. So in order to get the 4th term, I got to find the 2nd and the 3rd terms. Then I can get my 4th term. So my 2nd term, following my rule over here, I would take my previous term of negative 3 and add 6 to it. What does that give us? 3. So for my third term, I would take my second term, which we just found to be a 3, and I would add 6 to it. So what do we get for this one? 9. So then our fourth term, the one we're looking for, our previous term, which was a 9 plus 6, gives us a what? 15. So we got a choice for them, 15. So let's take a look at the back. So arithmetic sequences are relatively easy to spot. Again, all you have to do is look at each of your terms, see if they're increasing or decreasing by the same amount. So for example 3, our ABCD, we're going to first figure out if it's arithmetic or not. If it is, then we're going to fill in what the number should be that's in the missing spot. So let's look at letter A. What are we going up by each time? Plus 4 plus 4. So does that make that arithmetic? Yes, because it's adding the 4 each time. So then what should be our missing number here? 17. So let's look at letter B. What am I doing to get from one term to the next? Times 2. Is that arithmetic? No, not arithmetic. No. All right, letter C. How are we going from one term to the next? Minus 3, minus 3. Is that the same over here? Yep. Is that arithmetic? Yes, because it is still decreasing by the same exact amount each time. So then what is this missing number? Negative 2. Because 1 minus 3 would give us negative 2. And then our last one, letter D. What are we doing each time? Divide by 4. Divide by 4. So is that arithmetic? No. Not arithmetic. So finding a specific term in a sequence without listing all of your terms out can be kind of tricky, but using the formula that luckily you will be given on your reference sheet makes things a little bit easier. So let's look at example 4. We have the sequence 4, 14, 24. They're going to ask us to find some other terms of this sequence here. So first thing we have to figure out is what are we adding each time to get us through there? 10. So our common difference is 10 because we're adding 10 each time to get us to the next term. So part A wants to know, what is the fourth term? So using our formula, I'm going to write it down. Now I don't expect you guys to have this memorized. I do because I've been doing this for a long time. All you would have to do is go to the front, copy it down. So a sub n equals a sub 1 plus n minus 1 times our d. They want us to find our fourth term. So that means we're looking for when n is a 4. So I'm going to plug in 4 for all my n, so that gives me a sub 4. Looking at our sequence, the part they gave us, what was our first term? 4. And again, I'm plugging 4 in for my n in the parentheses. Also, every n gets a 4. And then we said our common difference was a 10, so I'm putting that in for my d. Always adding 10 each time. So now let's just follow our order of operations here. 4 minus 1 times 10 plus 4. So our fourth term would be 34. Let's try it for B. B wants us to find our 10th term. So now for our 10th term, our n is going to be a 10. And again, we're going to use that same formula that we just used in part A. So a sub 10 equals our first term, which is still a 4, plus 10 minus 1 times the common difference of 10. So then we'll follow our order of operations. What's 10 minus 1? 9. 9 times 10 plus 4? 94. So our 10th term is 94. So then for this one, C, they want us to write a recursive formula for a sub n based on the number, or based on the term number n. So recursive formula, even though they want us to use our other notation of subscript, still need your two parts. You still need to tell us what the first term is. You still need to write the other stuff. So our first term is 4. So a sub 1 equals 4. Our recursive, we take our previous term, which we remember in subscript is a sub n minus 1. You write that little n minus 1 there. That means our previous term. And we're adding 10. So your previous term plus 10 gets us to our next term. There's our recursive. D, they want us to write our explicit formula. So again, remember, when you're writing the explicit formula, you've got to use that formula that they gave you on your reference sheet. N is going to stay as an n, because we're just writing a general formula. Don't have a value for that. First term was still a 4, so I put 4 in for my first term. N minus 1 stays as n minus 1. Common difference for this problem is still a 10, so I put that in for my D. So we'll distribute. So I get 10n minus 10 when I multiply. And then we just got to combine our 10, negative 10, and our 4. What does that give us? Negative 6. So 10n minus 6. So our last example here, example 5, this is an example of a kind of problem that you would see on the regions where you just kind of have to think your way through it. We got seats in a small amphitheater follow a pattern where each row has a set of number seats more than the row before it. The first row has 6 seats and the fourth row has 18. How many seats does the last row, which is the 20th, have? Show your work to justify your response. So one way is I start writing my numbers. My first row they told me had 6 seats, so that's why I put 6 first. I don't know how many are in my second row. I don't know how many are in my third row. My fourth row has 18. So remember, since this is arithmetic, to get from one row to the next, I always have to be adding the same number. Kristen? 4. So 10 plus 4 gives me, or 6 plus 4 gives me 10, plus 4 gives me 14, plus 4 gives me 18. If you couldn't figure that out, does anybody think they know another way they could figure it out? You can't just see it. How many times did I jump from row 1 to row 2? Once, and then I jumped a second time, and I jumped a third time. So there's 3 jumps there. Can we agree with that? 1 row. 18 minus 6 gives me what? So there was a difference of 12, and I had to jump 3 times, or move 3 times. So that's how we get our 4 also. So you had to go up 4 each time to get you to your 18. There's other ways to figure it out. Whatever way works for you, that's what you want to use. So now to find our 20th row, we're going to use that formula that is on your reference sheet there. My first row has 6. My n is a 20 because we're looking for the 20th row. And we just figured out we are always increasing by 4 seats. So 20 minus 1 gives us 19. So what's 19 times 4 plus 6? 82. So the 20th row has 82 seats.